let's talk about titanium. You know, it's the stuff that makes jet engines and surgical implants possible. But this incredible material has a secret. It fights back. Today, we're going to dive into the surprising science that's finally taming the supermetal and how a few totally counterintuitive ideas are changing the entire manufacturing game.
Okay, so let's start with a decision that engineers in aerospace and medicine have to make all the time. Aluminum or titanium? One gets you lightweight performance, the other gives you incredible strength. But the real cost, the thing that can make or break a project, isn't just the price of the metal itself.
At first glance, the trade-offs seem pretty straightforward. I mean, this table lays it all out. Aluminum is light, it's easy to work with, and it's pretty cheap. But then you look over at titanium, and wow, its strength and resistance to heat and corrosion are just off the charts. The catch? Well, it costs more, and look at that machinability rating. Harder. As you're about to find out, that is the understatement of the century.
Right, so the real challenge, the one that keeps engineers up at night, isn't just picking the material. It's actually shaping it. Because unlike pretty much any other metal, titanium fights back hard.
When you try to cut a piece of titanium, you're not just carving some metal. You are entering a tiny, microscopic war zone. The very properties that make titanium so great are the same things that turn a simple machining process into a battle of attrition against your cutting tools.
So here's what happens. You've got this perfect storm of problems. Titanium is so strong you need a ton of force to cut it. Now, with most metals, all the heat from that force just escapes with the little shavings, the chips. But titanium is a terrible conductor of heat. So instead of going into the chip, all that intense energy gets funneled directly into your cutting tool, basically melting it and destroying it with shocking speed.
This whole heat problem was so catastrophic that the industry had to get really creative. It led to a strategy called high-efficiency milling, or HREM. But as we're going to see, an even smarter twist on this idea is now changing everything.
The idea behind HREM is actually pretty clever. Instead of taking one big, wide bite out of the metal, you take a very shallow cut on the side. That's your small radial depth of cut, but you use the entire length of the tool's cutting edge. This spreads out the heat and the wear, which lets you crank up the speed and get the job done faster.
And for a long time, that was the best way to do it. But then an engineer named Don Grant started asking a really basic question. Everybody just assumed that taking a smaller bite was the key to victory against titanium. But he wondered, what if the real villain here isn't the size of the cut, but just how fast the tool is spinning?
And that one question led to a strategy that sounds completely backwards. He calls it HREM, for heavy radial efficiency milling. And he just flipped the whole script. Instead of that tiny little cut on the side, you take a much bigger one. But, and this is the genius of it, you slow the tool's speed way down to compensate.
And this table just shows you the difference perfectly. Look at the data. With the old HREM method, you're taking a tiny 6% step over at a pretty fast 400 surface feet per minute. With HREM, that step over jumps to 27%, a much bigger bite, but the speed is nearly cut in half, dropping all the way to 220.
So what does that really get you? Well, here is the magic number. That simple change in strategy drops the peak temperature at the cutting edge by 361 degrees Fahrenheit. You go from a blistering 1,218 degrees, hot enough to destroy a tool, down to a much more manageable 857. That is a massive difference. And here's the absolute kicker. Both methods removed the exact same amount of metal in the same amount of time. You don't lose any productivity. But by rethinking where the heat was actually coming from, the HREM strategy makes the cutting tools last so much longer, saving money and making the whole process more reliable. Now, this deeper understanding of how heat works doesn't just lead to new techniques. It can also completely debunk myths that people have accepted as fact for decades. For years and years, the rule of thumb was simple. If you were machining any kind of titanium that wasn't the common grade 5 stuff, you had to slow down. By a lot, sometimes 30 to 50% slower. It was just accepted, a necessary evil to keep your tools from breaking. Except it's not always true. Researchers at Machino decided to actually challenge this old assumption. They compared the common, strong grade 5 titanium to the supposedly weaker grade 2, and what they found was pretty fascinating. So when we put the cutting force data side by side, we see something pretty remarkable. The chart on the left, that's the force needed to cut the strong grade 5 titanium. On the right, that's the force for grade 2. You can see the forces are lower for grade 2, but honestly, that's only half the story.
The real secret here is that grade 2 titanium is 2.4 times better at conducting heat than grade 5. It is much, much better at pulling heat away from the cutting tool. So what does that mean? It means to get the exact same 60 minutes of tool life, you can machine grade 2 nearly 3 times faster than grade 5. That old wisdom wasn't just a little off, it was completely wrong.
Okay, so we've gotten pretty deep into chip thinning and radial engagement and thermal conductivity. So why does any of this really matter? Why should anyone who doesn't run a machine for a living care?
Well, it's because this is how real innovation happens. When you really get the science behind the material, you can optimize your strategy. That makes you more productive and more profitable. And that, in turn, is what allows companies to design and build the more complex, more reliable, high-performance parts we all depend on, from better jet engines to life-saving surgical implants.
This whole journey into the science of the cut just goes to show you that true innovation isn't always about inventing some new wonder material. A lot of the time, it's about questioning the old rules to find smarter ways to shape the materials we already have. And it really makes you wonder, doesn't it? What other impossible materials are out there, just one clever idea away from being unlocked?